My name is Patrick Rowan, and this is my lab report for Lab 5 on Faraday's Law. So the purpose of this lab is to observe magnetic induction and the effects of Faraday's Law by analyzing data obtained by dropping a bar magnet through a roll of aluminum foil and comparing it to a computational model that we were given. The results obtained were that the experimental time was 1.25 seconds and the computed time was 0.86 seconds. So the fundamental physics principles utilized in this lab are Faraday's law, which states that a changing magnetic field through a loop induces a voltage proportional to the rate of change of magnetic flux, as seen in the equations here. Additionally, the Biot-Savart law is important, um, which states that a steady current produces a magnetic field about itself, with the equation given there, and also Newton's second and third law. The second law being force is equal to mass times acceleration, and then the third being that every action has an equal and opposite reaction. Um, so some assumptions we made in the procedure was that we could consider air resistance as negligible. The only forces on the system were the magnetic force and the gravitational force. The bar magnet acts as a magnetic dipole. And in the experiment, basically what we did was we took a bar magnet and we had our roll of aluminum foil. We dropped the magnet through the roll of aluminum foil and measured the amount of time it took for it to pass through. Um, the system would be considered the aluminum foil and the magnet. The surroundings would be everything else. So our experimental data that we measured were the dimensions of the tube, as well as the magnet mass and the trial time. So again, the measurement here was that it took 1.254 seconds for the magnet to fall through the aluminum foil. So here's the computational model, or at least the first section that has to do with the inputs for the mu naught over 4 pi, the resistivity value for aluminum foil, as well as the gravity constant. Additionally, there's the measurements for the tube, as well as the properties of the magnet. Here's where we get into the kind of nitty-gritty of the code. So we have the function that calculates the magnetic field of the bar magnet on the top left using the Biot-Savart law. We have the function that calculates the magnetic flux using Faraday's law. And then on the right, we have the relationship between the magnetic force as well as the force of gravity and the amount of magnetic field at each ring inside of the aluminum foil, since we considered um, the aluminum foil to basically be a concentric stack of rings, all of which participated in the creating the magnetic force which repelled the falling magnet. So here are computational results. Basically, these two rings on top went down to the bottom, just illustrating the currents that being formed as the magnet fell through. And we also have this graph which illustrates velocity over time, showing how velocity is constant for this period from about 0.15 seconds to about 0.85 seconds, showing that there was no change in acceleration, which means that F net was equal to 0. So interpreting the simulation by using Lenz's law, we know that the red in simulation is the counterclockwise current and the blue is the clockwise current. We know that if we flip the magnet, the same effect occurs, but the current directions would be flipped, again, by Lenz's law. The computational results are slightly faster than the real-world results. This is due to experimental error. And the gravitational force is greater than the magnetic force when entering and exiting the foil, but the same while within, again, because the F net must be equal to 0 because there's no change in acceleration. So again, potential errors we have were air resistance, friction, where if the magnet hit the side of the aluminum foil in our real-world experiment, it could have affected the results, as well as inaccurate measurements with our stopwatch of the actual. So with the what if questions, with the question that if the resistivity of the conductor were reduced as close to as possible to zero, this would change the dynamics of the falling magnet in that it would maximize the current because there would be no resistance, meaning that the magnetic force would be greater and the magnet would take longer to fall through the hole. And if holes or slots were cut into the tube, this would affect the ring currents in that there would be less ring currents because there would be less fully attached rings, which again would affect the magnetic force by reducing it.